Motion doesn't exist. Or that's what he said.
It goes something like this. Imagine shooting an arrow and freezing it at certain points in time. At this point, the arrow isn't moving. Same goes to here and here. So the arrow could never have moved. But if that's true, how did I end up here?
It wasn't until 2,000 years later when two people had an idea, but they argued over who came first. Their solution was a concept that would revolutionize the world as we know it. Let's talk about calculus, or to be more specific, derivatives. Obviously something's wrong here because... But how?
Well, take a look at this photo. Wait, not this one. Yeah, take a look at this photo. The car is frozen in time because it's a picture. But do you really think that it's not moving? You would say no, because of this trail behind. It showed that this car was fast, like it had velocity. So maybe we could find an indication of velocity. In other words, it's like taking a photo of the speedometer.
But the boys did not have a camera nor a car, nor a speedometer. So how did they figure that out?
Let's say this car is driving along a road. Vroom 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 vroom. Well, from the outside, we can't see the speedometer, but since we know the position at any given time, we can draw a graph on the XY axis, like this. So to calculate velocity, we first find 2 points, like this and this. So this is the distance traveled, and this is the time elapsed. Does this formula look familiar to you? Because we're actually finding the gradient of the line connecting the 2 points. But this is where we have a problem. You see, when we calculate a gradient, we need 2 points as reference. But we want to find it now at a specific point. And if we force both points to be the same, you get 0 over 0, which is... Imagine if we let 0 over 0 be a number. Let's say 69. Shut up, you're not funny. Okay, fine, let's say 1. So you can do normal stuff with it, like this. But wait, isn't any number multiplied by 0 also 0? So for example, this. And if we divide both sides by 0, we get... So we conclude with 1 equals 2. Uh-oh. Remember that we can do this with any number, so we will get absurdities like $5 is $50, 30% is 100%, and math as we know it will collapse, so will everything in the outside world.
And that's why math people ban 0 over 0. Where were we? Alright, so we cannot find the velocity with just 1 point like that. So that's it. Thanks for watching. We shouldn't just stop here, because we could still find an answer that is close enough.
So back to this graph. Let's say we want to find the velocity at x equals 5. So we fix 1 point here first, and find the point close to that. Let's say x equals 6. And then we calculate. Now obviously this isn't really close enough, so let's make it closer, and closer, and close. So notice what we're doing here. Since we couldn't have the 2 points overlap, we want the 2 points to be really close, but not touching each other. As we continue to repeat this process, we notice something interesting. The gradient seems to stop decreasing and settle down at some fixed value. In fact, it's as if this approximation is reaching some sort of limit. With these 2 points in mind, we want to focus on the difference in the x values and the y values. So we denote the difference in the y value as delta y and the difference in the x value as delta x. Here we are using the Greek letter delta, and it represents a change in some value. And if we look back to the graph, we realize that it's actually a function as well. So we can call it f of x. Each y value is actually an output from x. So we can denote delta y like this. Therefore, the gradient can be represented as such. Now recall that we want to keep shrinking the value of delta x to almost unexist, but actually not. And as we did that, the values seem to approach some kind of limit. So in mathematics, we write this notation of the limit like this. I wonder how the boys are doing. Oh hey, they've also invented their own notations for this thing. But we actually think this is better. You see, it looks like a fraction for a reason. Leibniz chose dx to represent a very small change in x, while dy likewise is a small change in y. Now notice that as delta x becomes closer and closer to 0, the line that we mentioned about becomes closer and closer to the tangent of the graph at that specific point. And to be honest, just simply asserting that the derivative is used to find the tangent does not do this entire concept justice at all. You know who I'm referring to. And just to recap once more, I'm not saying that delta x equals to 0. That yields an undefined result. Instead, what we're doing is finding a really sneaky way around this trap. So, we did it. Thank you for even sticking this far. Remember, we managed to discover this formula from scratch and all by ourselves. So now we can let people throw this formula into students' heads without any intuition whatsoever.
I cannot even describe how powerful this formula truly is. With this, we basically unlock the secrets to motion and prove the 2,000-year-old paradox wrong. But there are far more fields out there that have rate of change inside it that apply the derivative. But you may be asking now, how do I apply this formula? Is this really all that the limit is useful for? To which, stay tuned for my next video, which I'll be discussing those in further detail. Hopefully it won't take forever this time, but thanks for watching.
Once again, thank you so much for finishing this video. I intend to grow my channel, so if you enjoyed what you watched, please leave a like and subscribe to my channel. And also leave a comment if you have any suggestions as to how to improve it. And that's it for now. I'll see you next time.